Okay, so in this video, we'll be talking about the electric flux, which is about the Gauss law. First of all, I need to introduce to you what is electric flux. Electric flux phi can be visualized as the number of electric field lines penetrating through an area. That means that now let's say you are given an area, and then you know that the area vector is perpendicular to the surface area. Is perpendicular to the surface area itself. That means now you are given an area. The area vector must be perpendicular to the surface area at every point on the surface area. So now let's say that the electric field is parallel to the surface area element. And then the formula for the electric flux phi is equal to E dot A. That means that is equal to EA cos theta, where the theta is the angle between E and A. So now when E and A are parallel, the angle between them is 0. So cos 0 is equal to 1. So you know that the phi is equal to EA times 1, which is equal to EA. In another case, there is an angle between E and A, and then the angle, let's say, is now 60 degrees. The electric flux is equal to E dot A, which is equal to EA cos theta, which is equal to EA cos 60 degrees, which is equal to half EA. So now you see, when there's a non-zero angle between E and A, the amount of electric flux decreases. And then since phi equal to E dot A, that means that electric flux is a dot product. So we say that electric flux is a scalar quantity, and therefore electric flux does not have any direction. So if you are asked to explain what is Gauss law, this would be your answer. Gauss law states that the total electric flux out of an enclosed surface area is equal to the total charge enclosed by that enclosed surface divided by the permittivity of the medium epsilon. So total electric flux phi is equal to total charge over epsilon. And then may I know the formula for the electric flux? That is the closed surface integral of the electric field. Okay, when you are in a medium, then you use epsilon. When you are in the vacuum, you use epsilon naught. So may I know what is this mean? That means that what does this circle on the integral sign mean? Okay, first of all, let's say now you are doing a line integral, then it's just this, a line integral. But then when you want to do a closed line integration, that means that the line integral will form a closed loop, and therefore it will have an area. And so now let's say you are doing a surface integral. That means that maybe you have a surface and then you integrate the electric field with the area. So this is just an area. And then when you are doing the closed surface integral, that means that all the surface will enclose together to form a volume. For example, in this case, you have a circular area, another circular area, and also a side area. And therefore, you have an enclosed surface area to contain a volume. Let's say now, you don't have this area anymore. You cannot form a volume because your surface is not enclosed. Only when the surface are enclosed then only you can form a volume. So now it's the same thing happening here. You have to make sure that your Gaussian surface is enclosed to form a volume in 3D. So for example, let's say now you consider a point charge Q in the vacuum. You do an enclosed spherical surface, and then this spherical surface is enclosed. And then you are going to do this integration right now. For an enclosed spherical surface, for example this one, you know that the surface area vector is perpendicular on every point on the Gaussian surface. And then you also know that for a point charge here, the electric field will point out of the source. So you know that when the electric field is in this direction, dA is also in this direction. For any point on the enclosed spherical surface, for example, maybe this point, the E is in this direction. And then dA is also this direction. That means that E and dA are parallel to each other. So you know that E dot dA equal to E dA cos theta equal to E dA cos 0, which is equal to E dA. So you can get rid of the dot product here. And now the total charge enclosed in this surface is point charge Q. And then you know that the electric field strength at this point is equal to the magnitude of electric field strength at this point, which is also equal to the electric field strength at any point on the Gaussian surface. So E is a constant. When you are integrating a constant, you can get the integration. You can get the constant out of the integration. May I know what is the value of the closed integral of the surface area? That means that the total surface area of the sphere is 4 pi r squared. So you know that the electric field due to a point charge is E equal to Q over 4 pi epsilon 0 r squared. In the last video, we derived this from the formula of the electric field strength. But now you are deriving this from the Gauss law. So let's consider a uniformly charged conducting plane in a vacuum. So now you have a uniformly charged conducting plane. A uniformly charged means you cannot say that the charges here are more than the charge here. You cannot say that the charges here are more than the charge here because they are uniformly charged. So that means that the charges are uniformly placed on this plane. Okay, so now we recall the formula that you get from the Gauss law. When you are doing the closed surface integration, you are doing the surface integration for different surfaces. For example, now we consider a cylindrical surface. You have a top circular area pi r squared, and then another bottom circular area which is also pi r squared, and then the side area which is 2 pi r h, where the h is the height of this. And then you know that for the top circular area, the dA is here, and then the electric field is also this direction. So you know that E is parallel to dA for the top circular area. But then for the side area, this is the direction of the dA. And then the electric field here is vertical. So you know that the dA is perpendicular to E on every point on this side area. And therefore, you know that E dot dA equal to E dA cos theta equal to D EDA cos 90 degree, which is equal to 0. So you know that this whole term is equal to 0. But then, since E is parallel to DA on this surface and also this surface, therefore, you can get the dot product out. And now you have to know that this term here has the same value as this term here because they have the same circular area, and then they also have the same electric field strength here and here. So these two terms have same numerical value, and therefore you can simply sum them up. E is a constant on this surface, and also on this point on this surface, and also on this point on this surface. So that means that E is a constant on this surface. So you can get the constant out of the integration. Then may I know what is the area of this area? That means that the area of this one, we assign it by A prime. Okay, so now you have done for this left hand side of the equation. May I know what is the charge enclosed by the Gaussian surface? The charge enclosed by the Gaussian surface is only this one, the yellow color one. You cannot simply count every charge on the conducting plane because I really care about the charge enclosed by the Gaussian surface only. That means that I only care about the charge enclosed here. Okay, so now because the conducting plane is uniformly charged, therefore I assign a variable which is the surface charge density. That means that the charge over area. I know that is a constant because it's uniformly charged. So sigma is equal to the charge enclosed by the Gaussian surface divided by this area, which is also A prime, which is equal to the total charge of the plate, the total charge of the plate divided by the total area of the plate, total area of the plate. So you substitute the charge enclosed by Gaussian surface here, okay, which is equal to sigma times A prime. And then you realize that the A prime can cancel out each other. And therefore, what is the value for sigma again? Sigma equal to total charge of plate divided by total area of plate, which is equal to Q over A. So now you can get the electric field of a uniformly charged conducting plane. You realize that in this formula, Q is a constant, 2 is a constant, area is a constant, epsilon naught is also a constant. So therefore, E is a constant and E does not depend on any distance. That means the electric field here is equal to the electric field here, which is also equal to the electric field here, which is also equal to the electric field here, which is also equal to the electric field here, 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 and here, because E is just a constant. And then you know that all electric flux lines are parallel to each other. And then the electric field strength is constant everywhere. The direction of electric field is perpendicular to the conducting plane. And then it is out of the conducting plane when the conducting plane is positively charged. But then the opposite happens when it's negatively charged. That means that the electric field will point here when the plate is negatively charged. Okay? But then consider here what you have learned in the last video. For a point charge, we realize that the electric field strength is like this. That means that when R increases, E decreases. So you know that the electric field lines are diverging away from each other. And then in the last video, I also talked to you that the electric field strength can be visualized by how many electric field lines in a region. That means that now you choose this region. In this region, you have 1, 2. You have 2 electric lines passing through this circle. And then for this region, you have only 1 electric field line passing through this region. So you know that the electric field strength here is stronger than here. So now you choose a region. there are two electric film lines passing through this region. You choose another region. There are also two electric field lines passing through this region, so I can say that the electric field strength here is the same as the electric field strength here. Alright. So now we do a question. A thin conducting square plate with a length of 10 cm in free space has total charge positive 60 microcoulomb. Determine the magnitude and direction of the electric field. Then you use the formula of the surface charge density sigma, which is equal to the total charge divided by the total area of conducting plane. It is a square, so you know that the area is L times L. Okay, and then you use the formula for the electric field that you have derived just now, which is equal to sigma over 2 epsilon naught. So please explain the direction of the electric field line. The electric field lines are perpendicular to the conducting plate and point away from the conducting plane because it is positively charged. If it is negatively charged, then the field lines are still perpendicular but then point towards the conducting plane. Okay? Calculate the electric flux of the enclosed surface. The total electric flux is equal to this, which is equal to the total charge enclosed by the surface divided by epsilon naught. May I know what is the net charges enclosed by the surface, which is equal to this one plus this one and plus this one? That means that you simply sum up all the charges, then you can know the answer. And then the unit for phi is Newton per coulomb meter square, okay, which is also equal to voltmeter. Find total electric flux which passes through this enclosed surface. Okay, by the same reasoning, you just simply sum up all the charges divided by epsilon naught. Okay, now you are given a picture of the dipole, and then the black lines show the direction of the electric field strength. Now you have 5 different Gaussian surfaces. You have 5 different enclosed Gaussian surfaces. And then may I know which surface has no electric flux? So your answer is X1, X3, and X5 have no net flux. Why? Because for X1, the net charge enclosed by S1 is positive Q and also negative Q. Positive Q plus negative Q equal to 0. So that means that for every flux that comes out of the surface, there is an equal amount of flux coming into the surface. Okay? Then for S3 and S5, they contain no charges at all. So you know that for every flux coming in, there's a flux coming out. Same as here. When the Gaussian surface is infinitely away from the dipole, actually you can still have some very minor electric field line passing through it. So for this line, when this comes in, this comes out. So you still have no net flux. So the answer is S1, S3, and S5 have no net flux. Okay? But for S2, at least it has a net electric flux coming out of the S2 surface. For the S4, you still have a net flux coming into the enclosed surface. Now we consider a volume of charges. Okay, so this is an insulator so that the charges can be distributed evenly throughout the volume. If not, if this is a conductor, then all the charges will be repelled to the surface of the conductor. So when I know that this is a spherical volume which is distributed uniformly with charges, I know this is an insulator. Okay, so now I give you a new variable which is the charge density. Charge density equal to the total charge divided by the total volume of the spherical volume. When R is more than A, which is here, okay, R is a variable. I don't care the value of R as long as R is less than A. Okay, then I do a enclosed Gaussian surface. Okay, this is an enclosed Gaussian surface. Then you do your integration. The key point here is that the charge enclosed by this Gaussian surface increases when R increases. So you know that E is directly proportional to R. For R greater than A, that means that you do another Gaussian surface here. That means that the Gaussian surface is now outside the volume of the charges. So you know that no matter how the R increases now, the total charge enclosed by the Gaussian surface is still a constant, which is Q. No matter how your R increases again, the total charge now is still a constant. And you know that E is now inversely proportional to R squared. This is the same formula that you get for the electric field strength of a point charge Q. So now you can plot a diagram like this. For R more than A, E is directly proportional to R. But for R is greater or equal to A, the E is inversely proportional to the square of R. This is very similar for what you have learned in the chapter gravitation. Now we consider Gauss' law for gravitation. Just now you are considering Gauss' law for electromagnetism. Okay, so now you have a spherical volume of mass. For example, maybe this is the Earth. And then now you are going to find the G, which is the gravitational field strength. And then the key point here is that when the Gaussian surface is smaller than this volume, when your R increases, the mass enclosed by the Gaussian surface increases. So that you know that ultimately G is directly proportional to R. On the other hand, when the Gaussian surface is larger than this volume of mass, no matter how your R increases now, the mass enclosed by the Gaussian surface is still a constant. Therefore, you know that G is inversely proportional to R squared. The shape of this graph is similar to the shape of this graph. But then remember that in STPM syllabus, you don't actually derive G by using Gauss' law. You use another method. And then actually these two pages are not in your STPM syllabus. But then I really need to tell you because I think they are really important. In the next video, we will be talking about electric potential and electric potential energy. Thank you.